Alright, welcome back to Strife, doing some math. Today we'll be working with the fundamental theorem of algebra. Let's look at a few definitions. Multiplicity is when a root of a function appears more than once. It's also called a repeated solution. It's when you're factoring, you get x minus 1 and x minus 1. That means 1 appeared twice. And then we have irrational conjugates, so that's in the form a plus square root of b and a minus square root of b. They're the same expression, but they change the sign. Instead of adding, we're subtracting. They're always in pairs. Complex conjugates are in the form a plus I and a minus I. Actually, it should be a plus bi, a minus bi, complex roots. So the fundamental theorem of algebra says a polynomial function with degree n has n number of solutions. So if we have an x to the fifth, there'll be 5 solutions. So for example, x to the 16 minus 9x to the 10th plus 3x to the third plus 38 has 16 solutions. And then our next example has 5 zeros. And they could be repeated. So let's try to do it the normal way. So I know the answers are already right here, but we're going to do it the normal way. And we're also going to use our tools to help us. So in this example, since our roots or zeros can be repeated, it's going to be quite annoying, but we can use a graphing calculator to help us, or a graphing app. I couldn't find a very good graphing calculator app, so I found a graphing app instead, and it's called Desmos. If this would let me, there we go. DESMOS. Should be able to easily find it. Desmos graphing app. And you're able to put in your function, type it in, and then it graphs it for you. So let's look at our graph here. If I zoom out, so it looks something like that. And then we're going to zoom back in to our x-intercepts, and it looks like if I click on this, negative 1, 0, and 2, 0. So if I zoom out all the way, I don't see any other zeros. And since this is x to the fifth, we should have 5. So we have negative 1, and then we have positive 2. So what we're going to do is go back and do it the normal way. So we looked at our graph, and we know that negative 1 and positive 2 are roots. So let's go ahead and use, let's first find our p's and q's. So remember, p is the factors of our constant, so negative 14. So that is plus or minus 1, plus or minus 2, plus or minus 7, and plus or minus 14. And then q is plus or minus 1, which is our leading coefficient. So our p divided by q's are plus or minus 1, plus or minus 2, plus or minus 7, plus or minus 14. But we already know that negative 1 and 2 works, and yes, my answer is right here, but just to go through the work. So since we know negative 1 works, let's put it in. So our coefficients are 1, negative 4, 4, 10, negative 13, and negative 14. This represents my x to the coefficient in front of my x to the fifth, the number in front of my x to the fourth, x to the third, and so on. I'm going to create this, drop down the 1, and then we're going to multiply 1 times negative 1, and then we're going to add. So we're adding these 2 rows, and then we multiply anything in the bottom with our factor there. Negative 1 times 5 is 5, so we get 9, 9, or negative 9, 1, negative 1, negative 14, positive 14, and 0. So we know for sure it works. So remember, what happens is that these numbers become the new coefficients of our broken down polynomial. So that becomes, so here's my x plus 1 right here. And then we have x to the 4th minus 5x cubed minus 9x squared plus x minus 14. Okay? And now we're going to try 2. So, so that goes into my 1, negative 5, 9, 1, and negative 14. So I'm using my broken down equation now, using those as the coefficients. So when I do that, I bring this down, I get 1, 2, minus 3, minus 6, 3, minus 6. Did I mess up somewhere? Oh, it's positive 6, sorry. And then that's 7. 7 times 2 is 14, gets 0. Okay. Next step. So let's go up here. So we have our x plus 1 from before. Now we have x minus 2. And then what we have left is x cubed minus 3x squared plus 3x plus 7. Okay. Now our graph only showed us 2 real solutions. And that means we could have 3 imaginary solutions, but most likely we have 2 imaginary solutions and 1 other real solution that is repeated. I promise I'm not looking at this. Usually imaginary solutions come in pairs, but imaginary solutions can also be repeated. So, the easiest way is to use a value that we've already used before. And obviously I'm going to use negative 1 because I just circled it up there. So negative 1 again, but this time I'm using these as coefficients. So 1, negative 3, 3, and 7. So 1, negative 1, negative 4, positive 4, 7, and then negative 7. Obviously, because this is our 0. So, I now have x plus 1, x plus 1, x minus 2, and then my lastly is my x squared minus 4x plus 7. Okay, so we finally got into a quadratic. We can deal with quadratic with many ways. We can try to factor it, but find 2 numbers that multiply to 7 and add up to negative 4, that's not going to be easily factorable, so we got to use the quadratic formula. Negative b plus or minus the square root b squared minus 4ac all over 2a. If you haven't memorized this formula, now you really got to. I'm not going to sing this song, but you know what I'm talking about. Here's my a, b, and c. So I plug it in, and I'm going to get 4 plus or minus the square root of, I'm going to simplify it already, to negative 12 over 2. So remember, we have ways of dealing with negative square roots. This is 4 plus or minus I. I gets rid of the square root of negative 1, and then what's left is square root of 12 inside. But we can simplify it further to 4 plus or minus 2i root 3. So that's the square root of 4 times the square root of 3. So the square root of 4 becomes 2. And then we got I root 3. And of course we still have the 2 on the bottom. And then we reduce to get 2 plus or minus I root 3. Divided both numbers by 2. So my answers, or my roots, are x equals -1, -1, so there's my repeated 1, 2, and then 2 plus or minus I root 3, and that is all 5 solutions. So with a graphing calculator, this helps, and you will have a graphing calculator portion on your test. I will supply graphing calculators. Okay, here we go. Finish up this problem. So it asks us, do the roots appear more than once? Yes, because -1 appears twice. So that's what it means to have a multiplicity of 2. It's just saying that the root appears twice. Now, on the graph from before, what are my x-intercepts? My x-intercepts are only -1, -1, and 2. Those are my only x-intercepts. We do not include imaginary because they're imaginary, they're not x-intercepts. So let's look at the graph one more time, going back to Desmos here. So notice at -1 here is that the graph goes all the way, and then it doesn't cross the axis, but just touches it at a point and goes back down. That's called a tangent. Tangent is when it touches at one point but does not cross. It does not keep going. Now, on the other hand, at 2, it totally crosses. So this is not tangent. So tangent is that there's a tangent at -1, but not a tangent at 2. So let's go back to our notes. So that's what this kind of stuff is talking about. And it also tells you if a root is raised to an even power, then the graph is tangent to the x-axis. So once again, it touches at one point, but does not cross. If it's an odd power, then the graph crosses the x-axis. That's just something to look at. Okay, now we're going to write polynomials given roots. Now, just for example, this is our goal here. And if we factor this, we'll get x minus 7, x plus 3. So our roots are x equals 7 and x equals -3. Now, if they started the question with our roots are 7 and -3, write a polynomial. So what you would do is you would just say x minus 7 and then x plus 3, and then you would multiply. You would FOIL. And that would give you x squared minus 4x minus 21. That's an easy one. Let's go to the next example. Write a polynomial function that has rational coefficients, a leading coefficient of 1. And then given that the roots are 5 and -8. So we have a function that we're trying to write a polynomial, and we have 2 roots, so we're always going to write it in this form. X minus one of the roots, x minus the other root. So we have x minus 5, and then x minus h, which is x plus 8. We FOIL it, so we get x squared minus 5x plus 8x minus 40, and that becomes f of x equals x squared plus 3x minus 40. That's not, working with 2 roots, it's not bad. So I kind of mentioned before in one of the previous examples is that imaginary roots come in pairs, and it comes from these 2 theorems. complex conjugates and irrational conjugates theorem. And what it basically says, if you have, like, for example, if I have 3 plus 5i and that is a root or a 0, that means its conjugate 3 minus 5i is also a root. So they always come in pairs. And then the conjugate, the rational conjugate theorem just works with our square roots. So if I had 3 plus square root of 5, then 3 minus square root of 5 would also be a 0. So they always come in pairs. So let's do a example. So write a polynomial function that has rational coefficients, a leading coefficient of 1, given 2 and 3i are zeros. So we have 2, 3i, and then our conjugate negative 3i. So those are my 3 roots. So this is going to be, whoa, x minus 2, x minus 3i, and x plus 3i. Okay. Now, let's FOIL. And it doesn't matter which one you start out with, but I'm going to do these two first. I'm going to FOIL these first. So that's going to be x squared minus 3ix minus 3ix plus, oh no, that's plus 3ix. There we go. Minus 9i squared. There we go. So the 3ix's cancel, and then I'm left with x squared minus 9i squared. And remember, I squared is equal to negative 1. So I squared equals negative 1. So I'm going to replace I squared with negative 1, and I'll get x squared minus 9 times negative 1, which is plus 9. So I have x squared plus 9, and then we're going to multiply x minus 2, because that's what we had from before. And what it'll look like is x cubed minus 2x squared plus 9x minus 18. There we go. Stop giving me the check mark. There we go. So once again, x cubed minus 2x squared plus 9x minus 18. And that's our function. Alright, one last example. Write a polynomial function that has rational coefficients, a leading coefficient of 1, given 0 and 4 plus square root of 6 are roots. So we have 0, and then because of our, if we scroll up a bit, our rational conjugates theorem, we have 4 plus square root of 6 and 4 minus square root of 6. Please, pen, stop bothering me. That's it. Woo. 4 minus square root of 6. Those are my 3 roots. So I'm going to have x minus 0, which is just x. And then we have x minus 4 plus square root of 6. And then we have x minus 4 minus square root of 6. So I'm going to work down here somewhere. Just ignore these words here. That's just for 4.8, 5.8. So I'm going to work down so I can have some more space. So I'm going to FOIL all this mess up here. So the first 2 are x and x, so that's easy, x squared. And then we have we have x times this mess. So that is minus x times 4 minus root 6. And then we have minus x 4 plus root 6. And then we have and then we have the last two, which is its own FOIL. So I'm going to do that up here. So 4 plus square root of 6, 4 minus square root of 6, whatever. So I'll get 16 plus 4 square roots of 6 minus 4 square roots of 6 and minus the square root of 36. So I'll get plus 16 minus 6. Square root of 36 is 6. Okay, so let's clean this up a little bit. X squared, and then I'm going to distribute this x here. So minus 4x plus x root 6. And then we have minus 4x minus x root 6. And then plus 12. So this number here, and then this number here will cancel because that's a positive negative thing. So plus x root 6 minus x root 6, those will go away. So I'm left with x squared minus 8x plus 12. And then don't forget, we still have that x minus 0 back here. And remember, x minus 0 is just x. So the last thing we do is distribute that. And that is our function. Oh, sorry, 1 second here. 0, 0. This was actually 10. 16 minus 6 was 10.